Today we are having Arun Ram and very important topic for our seminar, Specializations of Macdonald Polynomials. So thank you everyone for coming.
Okay, thank you. Thanks to Slava and everybody involved for having me again. Actually, it's really good because it gives me motivation to sort of think through some things I wanted to think about, but I have always been putting off. And it worked. It worked. It made me think about them and sort of organize what's going on. All right, so I'm going to start with the symmetric Macdonald polynomials, which are called P lambda QT, or if I'm being more, there's a set of variables, which is actually n variables. So x1 up to xn qt. And although everything I'm going to say, I think it works completely in general type, but I'm going to stick just to GLN, type GLN for today. So these are indexed by partitions, where I will use the slightly more general version of partitions to be any increasing or weakly decreasing sequence of integers. So I want lambda 1 greater than or equal to lambda 2. And that's really the right place for to work, because these correspond to the weight lattice of GLN, and so the negative ones naturally occur. Okay, so Macdonald would always start sort of by writing the specialization square to try to convince us that we should study Macdonald polynomials. And the specialization square, so the bottom axis is the Q axis. So here, these two corners are 0, 0, and 1, 0. So Q is going from 0 to 1. And the top corner is P lambda 0, 1. And the first amazing thing is that this bottom corner point, if I'm thinking about that specialization, those are the Schur functions. So we'll label them slowly, Schur functions. And this point here is E lambda conjugate. So these are elementary symmetric functions. Elementary symmetric functions. And if I look at this top left corner, those are monomial symmetric functions. So we can write that monomial. And this upper right corner is very special. So these are called P alpha lambda in Macdonald's book. And by definition, that's the limit as t goes to 1 of P lambda of t to the alpha t. And these are the Jack polynomials. And certainly from where we'll write Jack symmetric functions. That, I think for Macdonald, those were a major motivational collection of polynomials in the whole process of producing Macdonald polynomials. So the next thing is that these, if I look at this right-hand axis, so this is P lambda of, so Q is 1 and T is arbitrary, that's still the elementary symmetric function. So it's constant all along that right-hand axis. And the similar thing is true up here, is that if I look at, so now this is T equal 1 and Q arbitrary, that this is still the monomial symmetric functions. So another incredible thing happens, and that is that if I look at this diagonal, then these guys are when Q is equal to T, and that's still the Schur functions. And then on the left-hand side here is when Q is 0 and T is arbitrary. And these are the Hall-Littlewood functions. Symmetric functions. And on the bottom of the square, we have when Q is arbitrary and T is 0. And these guys are, well, in Macdonald Macdonald always sort of posed it as a question of what is this bottom case, but now we understand that these are what are often called Q-Whittaker functions. Okay, so that's the picture, and maybe I'll do this because I want to refer to it sort of constantly. There it is. Okay, so that's the specialization square. So I find it helpful to look at I mean, you can't somehow get a handle on this game unless you look at an example as to what's happening here. So my favorite example is P210. So I'm working in 3 variables, x1, x2, x3. And this is a little staircase partition. And if you write it out in terms of monomial symmetric functions, you get M210, which is with coefficient 1. And then you get lower terms in dominance. So I'm going to get M111 is the only other partition in dominance. And I'm going to get a coefficient here, which if you look in Macdonald's book, you would get it as 1 minus t squared over 1 minus qt times 1 minus qt squared times 1 minus q squared t, sorry. And then 1 minus t over 1 minus q times 1 minus qt times 1 minus q squared. So you already see the shape of these. They've got these coefficients that are rational functions in q and t, and something miraculous already happens here that I want to stress, which is that if I change t to t inverse and q to q inverse, you can just watch it happen here. So I have to multiply the numerator there by t to the minus 2, and I have to multiply the numerator by q to the minus 2 and t to the minus 1. So altogether on the numerator, I've divided by t to the minus 3 and q to the minus 2. And if you divide the denominator by q to the minus 2 and t to the minus 3, you get this. It's 1 minus t inverse. And then in the second term, I have to divide the numerator and denominator by t and q squared. And so you get this expression. So that's just completely amazing. Is that what we've just observed is that when you change q and t to their inverses, it's just exactly the same polynomial. All right, so it really doesn't, it's exactly the same. If you change q to q inverse and t to t inverse, I mean, you should think of q and t as actual numbers, you know, say 3/4. Q and t are 3/4. So it's rather miracle when you change 3/4 to 4/3, it's just exactly the same polynomial on the nose. Okay, and the other incredible thing is that when you set Q equal to T, so you can just do it in your head, T squared and QT, Q squared T and QT squared, T and Q, Q squared and QT. When you set Q equal to T, well, it's claimed this was the Schur function, but this does not depend on T. Okay, it's rather a miracle. And depending on how you set up the theory.
Arun, can I ask a question?
Yes, of course, yeah.
First, hello. And,
Hello.
hello. So, why doesn't all of this, what you just told us, say that this square that you're showing us is not well parameterized? It's not a natural parameter space for these bases. That is the fact that, you know, along the top and along the right-hand side and along the diagonal, they're all the same. You know, it's just over parameterized or something. And you don't have the right square. You don't have the right parameter space for saying what the family of bases is.
That's certainly right. It is over parameterized. There are many points where the basis is the same. So I actually do think of it that way, is that if you give me any point here, P, a particular of Q and T, and get a new basis of symmetric functions. So when you read chapter 1 of Macdonald, you see 5 bases of symmetric functions. I don't know, P's and the P's
Right.
and the S's and the M's. And now I have an uncountable number of bases of symmetric functions, except that a few of them are equal here and there. But it's not an easy matter to tell when they're equal. So in fact, let's go along that a little bit more. And that is that this T to the alpha T here tells you that when Q is a power of T, something special is going on. And when you look at these denominators, you also see that when Q and T are, so in fact, this picture has some, so I usually like to draw it like this now, because on these curves, there's something that holds those curves together. The bases aren't exactly equal, but if Q and T are in a certain relationship with respect to each other, then the bases act a certain way. So in fact, I because of analogies with affine Lie algebras, I call those levels, that these green lines are the levels of the different bases. But okay, so that's our little introduction to so I want to now go to non-symmetric Macdonald polynomials. I mean, all of that, what I've just said, is certainly the way that Macdonald was telling us many years ago. And I've started to study the non-symmetric ones. So the non-symmetric ones are called E, following Macdonald, who wrote them down also. So we'll call this XQT, or again with n variables. So x1 up to xn, q and t. But now they're indexed by compositions, or more generally, you take any n tuple of integers. So that's the full weight lattice of GLN, not just the dominant weights, and you get a non-symmetric Macdonald polynomial. And so one of the first facts about this is that these E mu's are equal to x to the mu. So x to the mu for me is x1 to the mu 1 up to xn to the mu n, and plus some lower terms. So nu less than mu, and you'll have some constant here, which depends on q and t, and then x to the nu. So that tells you, that the set of these e mu's, as mu runs over all integer sequences, is a basis of the full polynomial ring. So I'm working Laurent polynomials in n variables. So in the same way that the p's were a basis of symmetric functions, the p's are a basis of all polynomials. And I would like them to be on the same footing as, you see, I have another basis, which is my x to the mu's, mu in Zn is another basis. And somehow now I have many bases to play with of just ordinary polynomials. And you can just as well ask, well, let's expand in terms of a different one of these bases here. All right, so now one of my favorite formulas from that point of view for the symmetric Macdonald polynomials is the following one, is that if I'm going to take a symmetric, if I'm going to compute a symmetric Macdonald polynomial, then what I should do is I should symmetrize normalization constant. So 1 over w lambda of t times the sum over the symmetric group of w. And then here I put a factor, which is this T van der Waals, you might call it, or I like to call it a C function, but, and then here you put E lambda. All right, so you want to symmetrize E lambda, but with respect to this funny symmetrization that involves the C function. So then you have a fact, which I will sketch how you get it later. But if you plug in q equal to 0, then this is just x to the lambda on the condition that lambda is decreasing, that lambda is dominant. All right, so that tells me that when I plug in p lambda 0t, I get, well, I can do this quicker by copying this. Pasting it here. And now all I have to do is change this E lambda to x to the lambda. And that, if you look in Macdonald, is the definition of the Hall-Littlewood polynomial. So this thing that we were looking at over here, this specialization at q equal to 0, if you choose to define your p lambda by symmetrizing the E, if you use that as a definition of p lambda, then this specialization is trivial. You just plug in the specialization of it's trivial knowing how to specialize the E, so it just moves the work to a different place. Okay, but similarly, then if you're like Percy and you're teaching a course in symmetric functions, you could put t equal to 0 and then copy the same formula and so I can put here t equal to 0. And when t equal to 0, that normalization becomes 1. And when t equal to 0, this disappears. And that's actually your favorite formula for the Schur function, is symmetrize with a Vandermonde in the denominator. All right, so you could use that as an excuse to look at the Schur function if you didn't know that before. And similarly, if I want to look at 1, 0, no, 0, 1, 0, 1, I want the top left corner. Then I'll get 1 over, oh, I better do it the other way. Right? Okay, so now what happens is that this t turns into a 1, and this t turns into a 1, and that makes this factor just disappear. And this E lambda, of course, in all of these examples, this E lambda is x to the lambda, because I've got q0. That, of course, is how you would define a monomial symmetric function. Is you symmetrize just a monomial, because the C function, the Vandermonde stuff has all disappeared. All right, so that gives you a feel for both what these look like, and it gives you my favorite formula for the P's. All right, so now I want to look at the specialization square for the E's. That's my next job, is can we make a specialization square for the E's? So let's write that. For E mu. So we just start going. We should look at E mu 0, 0, and we should look at E mu 1, 0, and we should look at E mu 0, 1, and we might expect that there's something funny here, that I should take the limit as t going to 1 of E mu t to the alpha t. You go on. So of course, if you start to study this, you need to look at an example. And so my favorite example is just when I have n variables and I'm looking at one box, just 1, 0, 0, 0. It's just the smallest one that you can look at. And in this, the formula is that this is xi times x plus 1 minus t over 1 minus q, the n minus I minus 1 times xi minus 1 down to x1. All right, so I have a very, very good formula for that. And I can go and I can sort of try to do what I did before and change everything, all the q's to their inverse and all the t's to their inverse. And what happens?
Arun, what's your I index here?
It should
Oh.
be EI on the left. It should
Yeah,
be.
sorry. You're absolutely right. Thank you. This should be 0,
1 in the ith position.
1 in the ith position, 0. Yeah. So that the 1 here is in the ith position of the sequence of length n. So it's still one box, but it's a box in the ith coordinate. Yeah, thank you. So when I change this, you can see that if you just switch q to q inverse and t to t inverse, it's not the same. It's not equal anymore. You have to, if you want to get actually the polynomial to be equal, you've got to put some factor to make it equal to what you had before. So it's just not true that, so let's write that in green here is that usually E mu of Q inverse T inverse is not equal to E mu of QT. So you have to be very careful about what you mean when you write E mu of Q inverse T inverse, because if you get it backwards, with P's, it didn't matter. You know, you could, but here you have to be quite careful. And the other thing that you notice right away is that if I take this E, which has a 1 in the I spot and zeros everywhere else, and I specialize Q equal to T, then I get Xi plus 1 minus T over 1 minus T to the N minus I minus 2 times Xi minus 1 plus down to X1. So this is also really different, is that E mu TT depends on T, right? So we're not going to have that wonderful purple line along the diagonal where they all turned out to be equal and they didn't have any T's in them anymore. It's just, they just depend. On the other hand, so, whoops. Not this. If I were to look at E, again, 0, 1 in the I spot 0, and I look at the alpha version of it, well, that is Xi plus 1 over alpha plus N minus I minus 1, Xi minus 1 plus up to X1. So the Jack version, the limit makes sense. There's no problem. When you actually try to do a Jack version of E's, you don't have any problems taking the limit, and you might as well look at them. Okay, so what it means is that we have to revise this guy a little bit, and draw a new picture, which would look something like, oops, that didn't make a good square. Let's try again. So I want one square here, and then I want another square here. Great. And those 2 points are exactly matching, of course. And here I have E mu 0, 0, and here I have E mu 1, 0, and here I have E mu infinity, infinity, which is what you get when you write your polynomial in terms of Q inverses and T inverses, and then set Q inverse and T inverse to 0. So that's what that means when I write that, is this means that i.e. Q inverse equals 0, E inverse equals 0. All right, and you can go around making your, looking at all yours, let's say, so here I have E mu of T is infinity and Q is not infinity. And on this one, I've got E mu of Q is infinity and T is, and here I've got E mu 0T. And here on the bottom, I've got E mu Q0. Okay, so that's what the new specialization square has to look like. You've really got to consider both parts of it. So what do we know, more or less, is is that we know something about this edge here, and we know something about this edge here. Oops, that didn't work very well. Let's just undo that. Okay, so we know something about this edge here, and we're going to be able to do the same kind of a thing on the other ends. So that's more or less what I know. And the basic things are mostly observed by Bogdan Yon quite some time ago. So these are essentially Iwahori spherical functions. And these things on the bottom are Demozor characters. And similarly, up here, these are some Demozor characters. And these guys are some version of Iwahori's spherical functions. And hopefully I can give you a little bit of feel. So slowly, we'll see how far we get, but as to what I mean by that. How come it didn't show up, my screenshot? Oh, there it is. It's just slow. Okay, so this is the new pair of pictures. Okay, great. So how do you go about studying this? So my first, the main thing that I rest on is the monomial expansion formulas. Because they give me the easiest information to look at. So what that says is that if I'm looking at an E mu, I have quite good formulas for expanding it in terms of ordinary monomials. So I'm not going to go through these formulas in detail because they involve combinatorics. It takes a while to set up. But it's a sum over T's, which you should think of as tableau or alcove walks or whatever your favorite kind of common crystals or whatever your favorite thing is. And then there's a power of Q, which I write as Maj plus of T. And there's a power of T, which I write as COVID of T. And then there's a factor, which I don't have room for here. There's a factor, which is the product over K in your tableau of 1 minus T over 1 minus Q to the shift of K, T to the height of K, X to the T. All right, so that gives me a formula for expanding my E mu in terms of monomials. And there's a similar formula, which is Q to the minus Maj minus of T, T to the minus COVID minus of T, the product over K and T of 1 minus T inverse over 1 minus Q to the minus the shift of K, T to the minus the height of K times X to the T. And you know, or you prove some things about this. You prove that Maj plus minus of T is always a non-negative integer, that COVID of T is always a non-negative integer, and this shift and height is always a strictly positive integer, and height is always the strictly positive integer. All right, so these two formulas, they give you two things. First of all, they immediately tell you that these specializations that I'm looking at, 0t, e mu, q 0, e mu, infinity t, e mu, q infinity, they all exist. All right, because I've set up the formula so that you can just look and see, oh, well, when t is infinity, this term goes to 0. And it's perfectly well defined. And so immediately I have combinatorial formulas for these guys. And we get combinatorial formulas for free. Formulas. Okay, so that's reassuring. We can sort of control what's going on. And when you look at these formulas, so maybe I'll copy this so that it doesn't disappear too quickly. Right, so when we look at that, we get another consequence, and these formulas give two things. So first of all, they give one of those things that I mentioned before, is that E lambda 0t is equal to x to the lambda if lambda is dominant. And they give you that E lambda 0t is equal to x to the lambda, infinity t is equal to x to the lambda if lambda is anti-dominant. Okay, so this is important, especially if when I mentioned over here Demozor characters, because I will later, if I have time, talk about Demozor characters. But if you already know Demozor characters, the way that you build a Demozor character is you start with an x lambda, and then you apply a whole bunch of Demozor operators. And you sort of have two choices. You can either start with the dominant x lambda, or you could start with an anti-dominant x lambda and build your Demozor character upside down, right? So these two results are actually important, because I have to sort of know that the e's are trying to be Demozor characters, at least in the limit, at least at the starting points, right? So I haven't got very far yet, but I'm making progress in getting going.
And Arun, you want us to think of those sums that were sort of unspecified over combinatorial data as being sort of parameterizing the basis elements in the Demozor characters, right?
Oh,
Is that how you want us to think of that?
I want to think of them that way, except that I don't know any actual modules that do the job for me. I mean, yes, I want to, but I don't actually know how to.
You don't
get
to.
Right, except in the limits. Of course, at t equals 0 or at q equals 0, then I do know modules for affine Lie algebras that work. But in general QT, I don't know how to.
Are your Madge and Coves actual defined, or they exist by induction, or are they like charge or some?
They're like charge. That's a good analogy. So they're simpler than charge. Actually, they're easier to work with than charge. But if you give me a tableau, then I have to do some machinations to calculate those Madge and, count the number of things that are to the left of this and above that, and do that kind of a thing. Yeah. Okay, great. So that gets me. So now let me tell you about the E expansion formula. So I really like this formula. So this is a formula for the symmetric Macdonald polynomial. And it says that the symmetric Macdonald polynomial is a sum over rearrangements of lambda. So lambda is a partition now, so it's decreasing. I'm going to sum over all rearrangements, and then I'm going to expand in terms of the e's. All right. And the coefficient is very explicit here. It's the product over I less than j, such that mu I is bigger than mu j, of t times 1 minus q to the mu I minus mu I plus 1, t to the v mu of I minus v mu of I plus 1 minus 1. So E mu is in the way here. Divided by the same thing, mu I minus mu I plus 1, t to the v mu I minus v mu I plus 1, without the minus 1. So the difference between the numerator factor and the denominator factor is that extra minus 1, and then that's times E mu. So maybe I should put an extra parentheses here. So that's the coefficient. It's very explicit. If I had several more hours, I would explain why that's a natural C function evaluation, but it's something that we can just write this down as a sum of these guys. But this tells us something very interesting, and that tells us that this, so the consequence is, oh, I didn't tell you what this V mu is, and I might as well do that, because, so V mu is a permutation, is minimal length, such that V mu acting on mu, so V mu rearranges mu into weakly increasing order. So this is an unavoidable piece of combinatorics in the theory of Macdonald polynomials. So you have to get used to V mu. But the consequence is that this gives me something quite important, and that is that if I take P lambda Q0, so Q0 means that I'm putting T equal to 0. And when you look at this formula, there's a T here. And so that immediately tells you that this is equal to E W naught lambda Q0. All right. Which for me is important, because I always found this bottom edge, P lambda Q0, a little bit mysterious. What was it? And what this tells me is that this P is really a fake P. That this P, which is on the bottom of the P specialization square, is really an E mu. So this Q Whittaker function, which you thought was a Q Whittaker function, is really a Demozor character. That's what I've sort of learned over. And that's why it started getting picked up in the affine Lie algebras, Braverman and Finkelberg and so on. You started picking it up as a character of an affine Lie algebra. And that's this transfer that we've just written right here. Okay, so that's, I forgot to ask you, Slava, when I need to end exactly. Is it 50 minutes or an hour?
It's it's an hour, but at the end we can make a pause and then you can continue if you have something to
Oh,
say.
okay. No, an hour is good. I just then I'll. Okay, so now I have another formula, which for me is the most important of all, which is the creation formula for emu. Or sometimes I call it the Intertwiner formula because that's what Cherednik called it. So it starts with sort of the basics. E0, 0 is just 1. So that's the simplest one. And then you have a recursion for either adding, you can use it either for adding or removing a box. It says that if you take the nth part and move it to the front and add 1, then that's equal to q to the minus mu n times x1 times your old emu, except with the variables cycled around and x1 multiplied by q inverse. All right. So this is a cycling formula that adds boxes if you do it forward and removes boxes if you do it backwards. So because of this +1, it'll add a box if you go from mu to mu +1, and if you go in reverse direction, it removes a box. So we use it both ways. And then finally, we have this thing that if mu I is greater than mu I +1, then I can permute the ith and the ith entry of mu, and that's equal to some operator, which I'll write as del I xi minus t xi del I plus 1 minus t times q to the mu I minus mu I +1 t to the, well, that's not so important what these exactly are, but they're very specific things, times e mu. Where del I here is your favorite difference operator. So you switch the two variables xi and xi +1, and then divide by xi minus xi +1. All right, so I have a very specific way of sort of generating one emu from another emu by either rearranging the parts or by adding a box or removing a box, and you can generate them all this way. And that's the creation formula. So another way to say the same thing, and I really like to say it this way, is that e mu is obtained from 1. So 1 is my base case up here that I start from. And I obtain it by acting by a whole bunch of operators in succession. So I'm sort of calling this whole thing tau I check, say, and I'm sort of calling this whole operation up here also, well, this is an operation that I call tau g check or tau pi check, depending on how. If you read my paper with Wei-Ying Guo, we called it tau g check, I think. Okay, so this is my creation formula, not my formula, but Cherednik's creation formula. And this should remind you, so this might remind you of two formulas. So the first one is a formula for Demozor characters. So the formula for the Demozor character says that the character of a Demozor module is equal to operators
Curious.
applied to x to the lambda. Right, so how do you get a Demozor character? Well, you have an x to the lambda and you apply a bunch of ugly operators. And I want that to feel similar to this. You start with 1 and you apply a bunch of operators. And so here, this is where W is SI1 up to SIL is a reduced word. Okay, so my other formula is a formula for Iwahori spherical functions. So that's a formula that's going to say that if I want the Iwahori spherical function, that you might write this way. So this is all living in functions on a p-adic group, that you should get it by applying t's to x to the lambda. All right, so very similar. So this is in the world of GLN over a p-adic field. And this is in the world of GLN over this function, this local field, C adjoint epsilon. All right, so, and that's these two specializations, this left edge and this bottom edge. One is for the Iwahori spherical. And so what we're saying, and these are both nice papers of Yon that worked on both of these. So the first statement is to say that this Demozor operator, di, and so I'm going to write some things that if you know what they are, they'll help. And if you don't, you should think that you should just understand that I'm trying to relate two different things. I'm trying to relate this Demozor operator and this tau. And they're not exactly the same. So I have to fudge it a little bit. And I'm writing in the fudges just so that I can write a good formula. But you want to work with it, then you can go figure out what the fudge is. So you don't need them for right now. So this is equal to tau I. Well, I want it, but I have to correct a little bit here. So there's a y to the minus delta I 0 alpha 0 check, plus a factor, which is 1 minus t times q to the something t to the something divided by 1 minus q to the something t to the something. Actually, let me write this as a c plus t, or rather it should be minus if I'm being careful, xi del I. Okay, so this is really a comparison formula. So that's how I think about it, is that this is a comparison formula between the Demozor operator and the intertwiner. And that's, if you want to compare Demozor characters and emus, you're going to have to compare the two operators. And so you work it out. You write down what's the comparison formula. And it's perfectly explicit comparison formula. And it gives you that at t equals 0, then I'm getting that this operator x to the minus lambda 0 di x to the lambda 0 is equal to this operator. Okay, so up to some little constants that you have to be careful of, it's telling you that E mu Q0 is a level 1 Demozor character. I forgot to mention that part of the reason that we know this is because these two numbers are positive. So that they vanish, you want to make sure that this vanishes when t is 0. And as long as you know that that exponent is positive, then that will vanish at t equals 0. This term disappears, this term disappears, and you get the specialization. So it's really very easy to specialize once you have the comparison formula. And the specialization tells you that up mu is a level 1 Demozor character. And I'll just come in. And similarly, the second thing says that if I want to compare, well, actually, the way I wrote it, I used T inverse, but switch your Hecke algebra around if you want it the other way. If you want to compare that and a tau I, then you get t to the half tau I check plus 1 minus t q to the something positive, t to the something positive divided by 1 minus q to the something positive, t to the something positive. So once again, once you have written down the comparison formula accurately, oh, I should say that it's really impossible to write these formulas very, very nicely unless you act on the e's. If you try to write this comparison formula on the x to the mu's, it's just impossible. It's just a horrible mess. But when you act on the e's, then this comparison formula is quite easy to derive, and it comes out. And so then you can say that this gives that at t at q equal to 0, then this t that's appearing in my Iwahori spherical function is equal to the intertwiner, and the specialization of E mu at q equal to 0 is an Iwahori spherical function. Just because you've compared the operators that generate. All right, I'll stop there. That's what I have to say.
Yeah, thank you. Let's thank the speaker.